Thank you very much for the invitation. And today I want to talk to you about a topic that I have been working and interested in for a couple of years. That is dualities or boundary corner configurations in supersymmetric case series and their brane constructions in string theory. So dualities have been changing a lot our views of quantum field theories. And there are various types of dualities depending on dimension of space-time and the amount of supersymmetry. So for example, four-dimensional S-dualities, 3D and two-dimensional mirror symmetries are the dualities in a parameter space of series. Another type of duality you can find along the RG flow, for example, four-dimensional cyber dualities, 3D and 2D cyber-like dualities, they are cousins. Or perhaps you can find several UV descriptions, not only two, but more, which may flow to the same IR fixed point. So in a two-dimensional case, this is known as trialities with 0,2 supersymmetric case. And there are many tests of dualities in quantum field series. So at the basic levels, the matching anomalies and phase diagrams are very useful, even for non-supersymmetric cases. But for supersymmetric cases, we have more exact tests of dualities. For example, the equivalence of moduli space of supersymmetric vacuum, or you may compute physical observables like partition functions or correlation functions in terms of localization technique. And moreover, these physical quantities can be understood at a higher level, where the algebras formed by local operators can explain why it is the case. So these tests of dualities lead to very non-trivial conjectures or properties of mathematical objects. And there are many, many applications in mathematics, including 4D n=4 S-duality, 3D n=4 mirror symmetries, and two-dimensional mirror symmetry are physical realization of geometric Lagrange duality, symmetric duality, or homological mirror symmetry, and so on. So it is interesting and a challenging problem to find out the reason and origins of dualities in QFT. So in other words, why do dualities hold, and how can we find the dualities? So it is a very difficult and tough question from directly studying a QFT. However, there are several progress and success from string theory. So many supersymmetric quantum field series can be realized as effective series or world volume series, as a world volume series of branes in string theory. And several well-established manipulations in string theory, such as S-duality, T-duality, deformation of geometries or brane configurations, can explain and sometimes derive dualities in QFT. So namely, the geometrical explanation of dualities can be obtained from string theory. So in this sense, duality is one of the most important features that we can learn from string theory. So the problem that I want to ask is the following. Can we extend dualities across the dimensions of space-time? So this can be achieved by introducing some extended objects that is a defects of various dimensions. So for example, suppose that we have two dual series in the bulk, T and T prime. So when we introduce a boundary, then a bulk series is subjected to boundary condition, and also additional boundary degree freedom can be added at the boundary. And then the action of duality is now extended, where we have duality between boundary condition B for series T and B prime for series T prime. Moreover, you can add corner configurations in bulk series. Then this involves as junctions of boundary conditions, two junctions of boundary conditions. And the action of duality is more intricate. So with a bulk, boundary, and corners. So today I want to discuss boundary corner dualities for 4D n equal 4 and 3D n equal 4 gauge series based on my works, including collaboration work with Ami Hanani and Davide Gaiotto, and works by myself. So let me start with 4D n equal 4 by a Mills theory. So the theory is fixed by data as a compact gauge group, compact Lie group as a gauge group G. But today I want to focus on unitary case UN. And this can be realized by n coincident D3 branes in type 2B string theory. So the world volume theory of this D3 branes, so these D3 branes are realized as n equal 4 UN supermills in such a way that the 10-dimensional space-time symmetry in type 2B string theory is now broken to SO1, 3 cross SO6. And these symmetries are identified with a global symmetry of the theory. So 4-dimensional space-time and R symmetry. And the theory contains bosonic fields as 4-dimensional gauge field and 6 scalar fields. So now corresponding, I use index I, ranging from 3, 4, 5 and 7, 8, 9. So theory contains bosonic actions, the two terms, Mills term and topological term. And we have gauge coupling and theta angle for each. And these two parameters can combine into a complex parameter tau. And the theory is invariant under shift of theta angle. That corresponds to T transformation of parameter tau. And it's a classical symmetry. Moreover, we have quantum mechanically, we have strong weak duality. This corresponds to S transformation of coupling constant tau. And S duality for UN case is a conjecture that the modular group generated by S and T transformation leads to the equivalent description. So suppose that we have a boundary at x6 equals 0 in my convention. Sometimes I denote by y equals 0. Then we are interested in supersymmetric boundary condition. So condition can be obtained by requiring that the normal component of supercurrent vanishes at the boundary. So in the presence of boundary, we cannot preserve full supersymmetry simply because the square of supercharges generate a translation, which is now violated by the presence of boundary. And maximally, we can preserve half of supersymmetry. And correspondingly, global symmetry is broken to SO1, 2 cross SO3 cross SO3. So now SO3 cross SO3 correspond to R symmetry. So 3D n equal 4 R symmetry as a half BPS boundary condition. And the 6 scalars now split into 3 scalar Y and X. So pair of 3 scalars. And there are two basic half BPS boundary conditions. So one is a Neumann boundary condition, where gauge field satisfy Neumann, Y scalars Y satisfy Neumann, and X satisfy Dirichlet. So this can be simply realized by introducing a single NS5 brane on which D3 branes end. So you can easily see that the motion of these 3 branes along C45 is still admitted, but 7, 8, 9 directions are killed as a position of NS5 brane. So another type is a Dirichlet or non-boundary conditions, which is a bit interesting. So now gauge field satisfy Dirichlet, Y satisfy Dirichlet, but X satisfy Naum equation. So for abelian case, so this commutator vanishes. Therefore, this is a simple Neumann boundary condition. So in this case, we simply call Dirichlet boundary condition. However, so for non-abelian case, this solution has a pole structure, and this is known as non-pole. And the boundary condition is realized by introducing single NS D5 branes on which D3 brane terminates. So these two basic boundary conditions completely preserve gauge symmetry or completely break gauge symmetry. However, general BPS half BPS boundary condition are more interesting to choose some partially break gauge symmetry, and they can be labeled by three data. So the first data is a choice of a subgroup H of G, which is an unbroken gauge group. So once choosing subgroup H, we can introduce further 3D degrees of freedom, so 3D n-equal 4 series on the boundary, which couple to the bulk H vector multiplet. So these two data gives us enriched Neumann boundary conditions. And the last ingredient comes from the Neumann non-pole boundary condition. So non-pole boundary condition has a solution as a simple pole, and this numerator is SU2 elements, and this fixes the embedding of SU2 into gauge algebra G. So in a unitary case, this row is nothing but a partition of integer n. So as we saw, the second data is nothing but the three-dimensional n-equal 4 series themselves. So let me quickly review 3D n-equal 4 supersymmetric series. So the Lagrangian of the theory can be formulated by two super multiplets, vector multiplet and hyper multiplet. And the vector multiplet contains bosonic fields as 3D gauge fields A mu and three adjoint scalar fields phi. And the matter fields described by hyper multiplet consisting of pairs of complex scalars X and Y. And in 3 dimension, abelian part of gauge field is dual to periodic scalar gamma. And this is called a dual photon. And the theory can be fixed by two data. So one is again, the compact Lie group as gauge group G. And a symplectic representation is carried by hypermultiplet compatible with the n-equal 4 supersymmetry. And the 3D n-equal 4 supersymmetry, which are 8 supercharges, are rotated by R symmetry SO8, and this split into 2 SU2 factor SU2 cross SU2H. And in 3 dimension, typical symmetry known as topological symmetry exists. So classically, this is a shift symmetry of dual photon, but quantum mechanically, this can be enhanced to non-abelian symmetry. An additional global symmetry is a flavor symmetry, which rotate hypermultiplets. And in the Lagrangian, there are 3 kinds of parameters. So for each gauge factor, we have gauge coupling as usual. And there are 2 types of supersymmetric deformations by introducing mass terms and Fi terms. So we have mass parameters and Fi parameters. And typically, theory has 2 branches of vacuum, of supersymmetric vacuum, realized as hyperkähler manifolds. So supersymmetric vacuum equation can be solved by setting adjoint scalar to 0 and turning off mass parameter. So this branch is known as Higgs branch and parameterized by hyper multiplet scalars satisfying hyperkähler momentum up condition. And the space is constructed as the hyperkähler quotient. And this space is classical. It has no quantum collection. So the another branch can be found by setting hypermultiplet scalars to 0 and turning off Fi parameters. And this space is known as Coulomb branch, and classically parameterized by 3 adjoint scalars and dual photon. But there are significant quantum collections of this space involving the non-perturbative monopole collections. And a precise or rigorous definition of this space was given by mathematicians as affine algebraic variety, Nakajima-san and BFN papers. And so 3D unequal force series have interesting dualities known as mirror symmetry. So this duality is between the two UV descriptions, and they flow to the same IR fixed point by exchanging the modular space of vacuum, global symmetries, and parameters. So this is a very non-trivial statement and phenomena, since classical Higgs branch is equivalent to the quantum Coulomb branch to the photometers. So if you are lucky, then you can find quantum Coulomb branch as classical Higgs branch photometer. So the simplest example is abelian mirror symmetry. So some of you might not familiar with this notation. So this circle corresponds to the gauge symmetry, and square is a flavor symmetry, and edges correspond to hypermerge bed. So the theory is U1 gauge theory with n hypermerge beds on the left, and this is known to be mirror to this quiver gauge theories correspond to the extended linking diagram. For the special case for n equal 1, we have a mirror symmetry between SQD1 and free twisted hypermerge spread. For n equal 2, we have a self-mirror situation, and the theory is called the TSU2. Okay, going back to the original problem. So what is the duality action on the boundary conditions? Well, the problem has not yet been completely understood.
Can I ask you a question?
Yes, please.
In your previous example, why you have extended thinking diagram? In your previous example?
This one?
Yeah, why you say that it's extended thinking diagram?
Well, so this thinking diagram, so we have a n-1 nodes here, and also right. this, we can take such an extended thinking diagram, right, like this form. So this is, this is a similar form of the just thinking diagram. That is not so, I mean, not exactly the same, but this corresponds to the shape of this quiver correspond to extended thinking diagram, n-1 extended thinking diagram.
Okay, so you mean that you should extra line connecting the first one and the last one?
Yeah.
Okay.
But there are many interesting quiver like this type, or but this is kind of simple case with associated to n-1, and but I mean, this is the terminology. You can forget about this now, but this is quiver gauge theory. But sometimes it is terminated n-1 quiver gauge theory.
So I thought that's related to a fine, so it's not related to a fine thinking diagram.
Okay, yeah.
Anyway, okay, yes, okay. Yeah.
So the problem is to find the action of S-duality on the boundary condition. So the beautiful stories are known for the case with theta angle to 0, set to 0. So namely, S transformation on the boundary condition are known in terms of string theory. And it turns out that the duality action has a mixture of 4-dimensional duality and 3-dimensional mirror symmetry. So let me quickly review this. So the idea is based on the famous brane construction of 3D n equal 4 gauge series, known as the Hanani-Witten construction. So introducing the 3 branes stretched between NS5 branes, and possibly we can introduce additional D5 branes intersecting with them. Then 2 data and 3 kinds of parameters can be easily understood in string theory. So gauge group and representation are associated to the vector and hypermerge spread, and these vector and hypermerge spreads arise from the spectra of open strings. So D3 DC strings and D3 D5 strings. So in a simple case with unitary group, these data can be fixed by numbers of D3 and numbers of D5. The three kinds of parameters are encoded by the locations of 5 branes. So gauge coupling constant is now encoded by the length of the 3 branes between NS5, or distance between NS5. And the mass and F5 parameters are the location of transverse positions of 5 branes. So therefore, the deformational parameters in QFT can be now manipulated by changing by deforming the brane configurations. And the deformation should follow the charge conservation. The charge is known as the linking number. And these charges are carried by each 5 brane. So depending on the references, the conventions are slightly different. So here I take the definition of linking number as the difference of the numbers of these 3 branes from right and from left, and addition of opposite type of 5 branes on its left. So simply, you can easily check that these linking numbers can be obtained, so red colored. Then we try to move the middle D5 branes on right, for example. So this guy tried to move here. Then by following the linking number, we find the creation of D3 brane here. And so this process is very non-trivial, like a creation or annihilation of D3 branes obtained by following the charge conservation. And this is a correct manipulation preserving supersymmetry. And another important observation is the action of the S-duality and S-duality in type 2 string theory. So S-duality in type 2 string theory can implement S-duality in 4-dimensional unequal positive permules and mirror symmetry in 3D unequal 4 gauge series. So given the identification of gauge series, then we can easily manipulate S transformation, S-duality in type 2 string theory, so under the S-duality, D3 brane is invariant. However, 5 branes are exchanged under S-duality. So therefore, you can find new configurations by taking this S-duality, and then can lead new field series from brane setup. And they are expected to dual each other. So previous example, abelian mirror symmetry can be easily now explained from this manipulation. So on the left, I have SQED with N hypermodal spreads, and another S-duality, you get this configuration easily. And this is nothing but the previous expected quiver gauge theory. You can also obtain dualities of boundary conditions. So on the left, I have UN gauge theory with Neumann boundary condition and 3D unequal 4 gauge theory is coupled to this. The theory is known as TSUN. And performing S-duality, we get this configuration on the right. And this configuration defines the Dirichlet boundary condition for UN gauge theory. So I could not explain detail, but the linking numbers here correspond to the third data of boundary condition. That is nothing but the embedding of SU2 into G for the partition of N. So this has a trivial number. So therefore, we get the Dirichlet boundary condition. So this is a duality between 4D, 3D system and 4D without any 3D degrees of freedom. So far, the story was obtained by that Witten's work. So here I would like to generalize the duality, the wave of dualities by considering quarter BPS corner of 4D equal 4 and half BPS boundary of 3D equal 4. That is 4D, 3D, 2D system. So are there any questions so far? Good. So there are subtleties of supercharges in 2 dimensions, depending on the chirality of the spinors. So now we are interested in 4 supercharges, which is the maximum supersymmetry that can be labeled by integer p. So we have chirality p and 4 minus p. And typical examples are chiral supercharges, 0,4 case, and non-chiral supersymmetric case, 2,2. And in this talk, I want to focus on the 0,4 case to get new dualities in terms of branes. But I want to also mention about dualities conjectured from QFT analysis for 2,2 case finally by computing index. So the problem is to generalize Hanani-Witten configuration to understand corner and boundary. So this cartoon shows that, so we expect to have some object like this guy defining the corner of 4D and the boundary of 3D, which spans along 0, 1, and 6 directions, but localized along x2 direction. So 0,4 configurations, the object are 2 types, NS5 prime branes and D5 prime branes. More generally, they can combine into a PQ5 branes. And if you set a single NS5 prime branes, so again, so we can follow the degree of freedom, the transport directions of the 5, so these 3 branes, then we can check that this can be compatible with a Neumann for vector and Neumann for hyper. If you set a single D5 prime branes, we get the opposite type of boundary conditions, like non-for boundary condition for vector and dirichlet for hyper. But we should know that what type of gauge series emerge. I mean, 2-dimensional gauge series emerge from more general configurations, because as we saw, the data of boundary conditions include the boundary series themselves. So in this case, we would like to understand the 2-dimensional 0,4 gauge series appearing from more general configuration, which is a brain box model, surrounded by NS5 brain. And in the work with Ami Hanani, we try to understand the series by taking T-duality. So taking T-duality along x2 and x6 direction, we get a D1 branes with KK monopoles. And transverse selections, as usual, are Airy spaces. So the problem is to understand the spectra and the series for D1 branes on an Airy space. So C2 mod ZK cross C2 mod ZK prime. And this can be achieved by using a technique, auto technique by Douglas and Moore. So starting from flat space descriptions, so D1 branes propagating on flat space, which is described by 2-dimensional n equal 8,8 UN super mu series. The field content R is 0,4, 0,2 chiral merge spreads. I denote by R, L, U, and D. And there are 3 Fermi merge spreads, delta, nabla, and lambda. And using a technique of Douglas-Moore, we can compute a spectra. So how the gauge fields modify and how matter contents are modified. And as I show here, so 4 chiral merge spreads split into pairs of vertical lines, edges, and 2 pair of horizontal edges. And 3 Fermi merge spreads split into adjoint and bifundamental diagonal arrows, diagonal edges. So using this, we can identify what field theory, what field content arise from the brain box configuration. So each box of D3 brain, we have 0,4 vector merge spread containing 0,2 vector and 0,2 adjoint Fermi. From the horizontal and vertical arrows, we get hyper and twisted hyper merge spreads. And similarly, from diagonal edges, we get the Fermi multiplets. And also you can easily find the interaction terms by following the triangles formed by chiral and Fermi multiplets. And in addition, you can introduce flavored D5 and D5 prime branes. And then as you briefly explained, so we can follow the linking number and try to deform the configuration. And then we see the creation of these three branes, and we can identify the spectra arising from D5, associated with D5, D5 prime branes. However, this is not the end of the story. This is because we have serious issue of anomalies for 0,4 series. So given these configurations, so at the middle, I have U1 gauge group and adjacent boxes are, so some numbers I introduced like U to NTL or NT, so on. And they are global symmetry or flavor symmetry in the theory. And then I can evaluate the anomalies from this brane setup by using the previous identification of field content. Then it can be easily checked that we have gauge anomalies and global anomalies or drift anomalies. So in order for theories to be consistent quantum mechanically, the gauge anomaly has to be canceled out. So this strongly indicates that we have missing ingredients are in this configuration, and seriously associated the junction of NS and S prime branes. And actually, we are realizing that this can be beautifully canceled out by introducing the Fermi multiplet living at the junctions of NS and S prime branes. So we conjecture that there should be determined Fermi multiplet, so which are charged on the plus plus in the one diagonal and the minus minus for the another diagonal. In fact, using the identification of field content, we discovered a number of dualities associated with corner configuration and boundary configurations, including the work with Davide Gaiotto and works by myself. So there are too many examples. So therefore, I will show several examples here. So one example is a corner of 4D unequal positive biomills. We have junctions of NS and S prime branes. So the situation is the following. So we have four types of 4D unequal 4 corners satisfying the Neumann and Neumann, so pair of Neumann boundary conditions. In addition, we have hypermultiplet by fundamental hypermultiplet and twisted hypermultiplet, and two-dimensional Fermi multiplet correspond to diagonals, and additional determined Fermi living at the junction. On the right, so we have, under the S-dual transformation, we get this simple configuration. And then this theory has a 4D unequal 4 UN gauge theory in a whole four-dimensional space. And in addition, we have fundamental hypermultiplet coming from D3, D5 string, and fundamental twisted hypermultiplet arising from D3, D5 prime strings. And the last piece is the neutral Fermi arising from D5, D5 prime string. So this is a conjecture that we can obtain from string theory by using a previous identification of field content. And later I will show this can be checked by computing index. And another interesting type of corner is Y junctions, the so-called Y junction, where I have 105 brane, 015 brane, and 115 brane. So story actually depends whether N and M, so N and M are equal or not. So maybe I don't discuss detail, but okay, maybe the case with n equal m case is simple. So if you have n equal m, then first of all, so this configuration can be understood as T junction. I mean, T junction like this. I mean, this 115 brane is effectively understood as Neumann deformed by Chern-Simons coupling. So therefore, now the situation is that, so if m equal n, we have two types of UN gauge, so n equal 4 gauge series in the upper half plane and lower half planes. So on the upper half plane, I have UN gauge series with Neumann, and on the left, so the lower half plane, I have UL supermuse with Neumann. And in addition, I have fundamental hyperMOSFET coupled to UN gauge series. But now this satisfies the Neumann because of this guy. So now I have two types of UN gauge series and also fundamental hyper satisfying the Neumann. And the gauge anomaly is cancelled by Chern-Simons coupling associated with this 115 brane. But this contribution gives gauge anomaly in the lower half plane. So therefore, we have additional fundamental Fermi canceling the gauge anomaly. So this is the case with n equal m. Anyway, we have an interesting triality in this case by permuting integer L, M, and N. And performing a topological twist known as geometric Lagrange twist, we can get interesting vertex algebra, so-called Y algebra, studied by Gayot and Abchek. And I will briefly mention about the application to algebra in terms of index computation later. So without any 4D degrees of freedom, we can also discuss duality of boundary condition for 3D n equal 4 gauge series. So without this guy or this guy, they are the previous examples. So namely SQED and quiver gauge series. But introducing NS prime or D5 prime, D5 branes, we have boundary conditions. On the left, I have Neumann boundary condition and additional Fermi appearing from the intersecting D5 and S prime. And on the right, I have simple boundary condition, Dirichlet boundary condition given by D5. And this is a conjecture obtained from string theory again. And similarly, performing the topological twisting, in this case, we have two SU2 factor, SU2H and SU2C. And using one of them, we get the H twist or C twist. And then we can think about interesting mathematical ingredients as a vertex algebra associated with these topological twists. And this boundary vertex algebra studied by Costello and Gayotto, and subsequent one Costello, Croix, and Gayotto. Okay. So are there any questions so far? No question? Okay. So then I want to discuss how to check these conjectures from string theory by computing index. So supersymmetric index, so concerning superconformal field series, then we can define a supersymmetric index by the trace over the Hilbert space on the sphere in the radial quantization. So this is a function. So index is a function of formal variable xi and q in this convention here. And these formal variable q and xi are coupled to charges in the theory. So, and these charges are commuting with supercharges. And the space, the Hilbert space, can be also identified with a cohomology of supercharges we are interested in. So here, F is familiar for you, the Fermi number operator, and delta is defined as the anticommutator of Q and K dagger, and Fi are some global symmetry charges. So this is sometimes called a Hamiltonian definition. So this takes the same form as trace definition of Witte index. However, this index can be also evaluated from the Lagrangian description. And this can be identified with S1 cross so circle times sphere partition function. So accordingly, so index makes sense even for non-conformal series. So by considering S1 cross SD-1 partition functions. And the index does not depend on the RG scale. So therefore, we can compute this object from the UV descriptions. And using the localization technique, this can be evaluated by enumerating BPS local operators, the product local operators. So in this sense, this counts the local operators. But there is a generalization of supersymmetric index to study the boundary conditions, the half BPS boundary conditions. So which is, I now briefly explain. So that index can be computed by enumerating the local operators. And then now try to count the enumerating the local operators compatible with the UV boundary conditions, supersymmetric boundary condition. We can define half index. So this effectively counts the local operators in the bulk and on the boundary. So four-dimensional N=4 theory setup, this was studied by Yanko Lee and our papers to test the dualities of boundary conditions and the interfaces in four-dimensional N=4 superMUs. So I could not discuss details and much about this story, but for 3D N=2 series, the study of half indices are very interesting, and many authors try to study this. So, and there are many applications, not only in physics. For example, these ingredients, half index itself has interesting mathematical objects like a topological invariance or some very interesting Q series. But today I want to discuss further extension, which is quota index. So to study quota BPS corner of 4D=4 and half BPS boundary of 3D=4, we define the quota index. So definition is take the same form as usual ordinary index. But we try to count and enumerate the BPS local operators living in bulk on the boundary and at the corner. And let me emphasize that this is nothing but a generalization of half index and regular ordinary index in the sense that, so if we have empty bulk, 4D bulk theory, the quota index reduces to half index of 3D N=4 theory. And if we have empty 3D bulk series, this turns out to be the simplified, just elliptic genus for two-dimensional series with 4 supercharges.
May I ask a
and quota, yes, please.
So can you introduce briefly, typically what's the technique you use to compute these indices, like half integer, also quarter integer?
So technique is so I mean, so given this trace definition, we know what type of the local operator in supermarket has contributions. Then there are many techniques to derive quota index. So what type of contribution we can get? For example, Higgs mechanism, so Higgs mechanism manipulation is turn off some waves of the scalars. Then we should specialize some fugacities of the index that we can get consistent contribution to the index. But there are many consistent check of the derivation. The one I think a concrete example is to just follow the localization and derive explicitly.
I see.
But I will show what type of ingredients actually appear in this computation, and by using the examples. So maybe later I can tell you precisely how we get consistent building blocks of quota index.
Mm-hmm. Okay, so another question is, So the index, physically, sometimes it can be used to compute black hole entropy and so on. So is there any kind of physical application for the half index or the quarter index?
Yeah, that is the next this slide, right? So I will come to this. So here, so I have just a list of the applications to physics. So one example application is to study non-particle phenomena, including duality, the test of dualities, as we are now discussing, and symmetry enhancement or wall crossing phenomena. And also this can play a role of building block of some partition function on compact manifolds. So as you mentioned, so in the larger limit, index will be interesting to have some holographic interpretation. So far, I have no concrete example to see holographic check to have some holographic interpretation. But yeah, in some special cases like Y junction, we can get certain characters of the vertex of the algebras, and that can be checked in terms of holographic picture. I think yeah, maybe I will come to that later, showing the index computation like explicitly. So there are another motivation in mathematics. So this quantity itself is an interesting Q series with coefficient being Laurent polynomial in other fugacities. And the identities we can get from the dualities of conjecture from string theory is very, very non-trivial. And most of them cannot be rigorously proven. So therefore, it is very challenging problem to prove the conjectured identity from string theory. And also, by taking special fugacity limits, we can get the characters, the graded characters of some algebras formed by the local operators. So photo index has interesting two specialization of fugacities corresponding to two topological twists, H twist and C twist. So for example, 0,4 configurations, we can get the vacuum characters of corner or boundary BOA. Or you can think about 2,2 configuration, then this gives us certain characters of quantum algebras I will mention later. So this, so specialization of fugacities gives us the alternative discrete derivation of the characters of the algebra. So therefore, this gives us access to categorification of like equivalence of indices in terms of the algebras.
So can I ask you a question?
Yes, please.
Yeah. So in general, is there some modular property associated to the index?
So 2,2 case, the modules of the algebras can be defined by the boundary conditions. So therefore, this is a strong, the boundary condition is an ingredient to specify the modules of the algebra.
Yeah. So sorry, I mean my question is like for elliptic genus, it's a Jacobi modular form, but here you have some generalization of elliptic genus. So,
well,
so I do have some.
This is not precisely. I mean, so yeah, but I'm talking about the algebras are so okay. So the character of the algebra, so the character of some algebras are now formed by local operators in a gauge theory. So this is not precisely the same as so like yeah. So for example, the BOA or quantum algebras are kind of new ingredients in gauge theory setup. So I have no idea to think about like regular
actually,
ordinary
I just have a very naive question because in the modular forms you can expand in terms of power series in Q, for example. But then if you resum the power series, you have some interesting modular properties. So I was just wondering if your indices here.
Yeah, I agree. Yeah. So yeah, I think the modular property of these objects are very interesting question. So I think yeah.
Okay, thanks. Yeah.
Okay, so here are the examples of quota indices. So I'm running out of time. So maybe I will quickly explain. So if I have like Neumann corner configurations, so this preserves the gauge symmetry at the corner. So therefore, this can glue some corner configurations by using this building block. And if we have Neumann non-pole type corner configurations, then we have no gauge symmetry at all. So the index is just a formal product. And by taking the H-twist limit in this case, this becomes the character of W algebra. So this is a simple example to have non-trivial characters emerging from the corner configuration. And without any Fourier degree of freedom, we can think about the half index of 3D n=4 series. And this is an example for Neumann half index for hyper and Dirichlet half index for hyper. And then taking the limit H twist or C twist, we get the characters of symplectic boson for Fermi currents. So by combining all the ingredients, we can get very non-trivial algebras at corner or boundary, and then we can compute characters by taking these limits. Okay, now, so today I want to focus on the dualities of the corner boundaries. So then this is an example of the computation. So as I showed in the previous slides, we have dualities between these two corners. And so we can list up all the ingredients in these configurations, and we can compute the quota indices. And then amazingly, these precisely match with each other. And also, this strongly support our conjecture, namely the presence of determined Fermi merge bed at junctions. So without this ingredient, so identity does not hold. So this piece is very important and consistent. So for Y junction, so also indexes are slightly complicated, but we can check that this quota index has a nice triety symmetry by permuting integers L, M, and N. And also if you take H-twist limit, this becomes the characters of the Y algebra studied by Gayot and Lapchek. So in the case of boundary for 3D series, I can also compute half index in this case. So on the left, I have Neumann, so therefore gauge symmetry is preserved. So therefore I am collecting the protected operators with the gauge invariant protected operators by performing contour integral. But on the right, this is a Dirichlet boundary condition, and we have no gauge symmetry at all. But there is a significant non-perturbative collections associated with the monopoles. So this corresponds to infinite sum over the magnetic fluxes M1 blah blah MNF minus 1. So we have additional non-perturbative monopole contributions. And amazingly, these indices also match. So without 4D and 3D, we can see the dualities of two-dimensional 0,4 series. So this is the simplest duality, I think. So on the left, I have U1 gauge series with 1 hyper and 2 Fermi. And then this can be evaluated by ZK residue prescription. And it turns out that it is equivalent to simple Fermi index. So therefore, this is evidence of duality between U1 gauge theory with 1 hyper and 2 Fermis and free fermions. Okay, so far I have been discussing 0,4 configurations. So finally, I will tell you n=2,2 configurations. So, namely, 2,2 boundary conditions in 3D n=4 gauge series. So, so to talk about such application of 2,2 stories, slightly I will review some backgrounds of 3D n=4 gauge series. So as I mentioned, 3D n=4 gauge series admit hyperkähler moduli spaces. And then we have 3-kähler 2 form, omega 1, omega 2, and omega 3. And then we can define the symbolic 2 form, capital omega, by choosing a subalgebra n=2 subalgebra. in terms of this, we can define the Poisson brackets and defining the commutative ring, the Poisson algebras. And they correspond to Higgs and Coulomb branches. These chiral rings are called Higgs branch chiral rings and Coulomb branch chiral ring. And mathematically, these can be quantized by replacing commutative brackets with the non-commutative brackets. And physically, this can be achieved by introducing omega deformed planes. And the resulting objects are called quantized Higgs branch algebra and quantized Coulomb branch algebras. And they typically take a form of a shifted Yangian. For example, if I take Kuiper gauge series obtained from brane setup, so this takes a form of center quotient of shifted Yangian of SLn+1 labeled by partition. So 2,2 Barnett condition actually define the modules of these quantized algebras. So therefore, if you compute half index preserving 2,2 supersymmetries, they turn out to be the characters or modules of these quantized algebras. And another motivation to study these half indices are again the building blocks of some partition function on compact manifolds. So I cannot to talk in this talk, but the sphere partition function and correlation functions can be algebraically constructed in terms of bar module characters or twisted trace of bar modules. So in the work with Davide Gaiotto, we discussed. So therefore, bar modules can be realized some Barnett condition n equal 2,2 Barnett conditions. Then computing half index, this can play a lot of building blocks by grouping half indices. Okay, but in this talk, I want to discuss the dualities. So let me finally tell you about that. So far, duality has not been studied in the brane setup from the brane setups, but from the quantum field theory analysis, the dualities are conjectured for abelian cases. So in abelian gauge series, there are three basic Barnett conditions, which are Neumann Barnett condition and generic Dirichlet Barnett condition and exceptional Dirichlet Barnett conditions. So Neumann Barnett condition generically breaks down topological symmetry. And a generic Dirichlet Barnett condition means that we take generic waves of hypermolar spreads, and which breaks down the flavor symmetry. However, if you choose specific waves of hypermolar spread, then Dirichlet Barnett condition can preserve both flavor and topological symmetries. And the conjecture for Barnett condition is as follows. So Neumann for theory T is dual to generic Dirichlet for mirror theory T prime. And the exceptional Dirichlet for theory T is conjecture to be mirror to exceptional Dirichlet for mirror theory. So you can see the map of the global symmetry like this. So I computed half indices with 2,2 supersymmetry. Then I found that, for example, I will show the SUQED2 case, so TSU2 case, and then the half index of Neumann actually coincide with Dirichlet half index, generic Dirichlet half index. However, exception Dirichlet are slightly interesting. So indeed, I found a matching of indices for a special type of exception Dirichlet, but it is not so simple. For example, so other type of exception Dirichlet have interesting transformation. So it takes a formal linear combination of mirror half indices. And for exception Dirichlet half indices, so we have a nice mathematical identification. So namely, half index with exception Dirichlet Barnett conditions are identified with mathematical functions studied by Aganachiki and Okonkwo. In a transformation, mirror transformation we found is nothing but the change the basis of vertex function performed by elliptic stable envelope proposed by Agnagic and Konko. So therefore, the mirror transformation of half index with 2,2 supersymmetries may be understood by considering such a stable envelope. But I only look at the abelian case here. So this is interesting to see non-abelian cases further. Okay, let me conclude. So we have discovered various dualities of boundary corner configurations for 4D nickel 4 and 3D nickel 4 series using the brain setups. And we have introduced new type of index we call quota index, which count the local operators in the bulk, on the boundary, and at the corner. And they have many, many applications in both math and physics. So since I have run out of time, so maybe I will stop here. So I have listed up many future works we can do. Okay, let me stop here. Thank you very much.
If anyone has questions, can you unmute yourself?
So I have a question related to this 3D case. So you have the structure of a chiral ring, and usually this can be related to some integrable model by the work of Nikolsov Shatashvili. So I want to know in this new corner duality and these indices, is there any interpretation in terms of integrable models?
Yeah, I think this is a very, very interesting question, but I have no answer to this. But in the case of boundary condition, I mean, 4D with boundary, not corner. So recently, Tedchenko white paper discussed such an interesting integrable application to integrable system. But the corner cases, so we found recently, but nobody. Yeah, I think algebras have been studied a lot, but I don't know immediate answer to this question. But as you say, this is very interesting to understand whether we can have some application to integrable system.
Yeah, that would be very interesting. And a somewhat related question is, some of these indices, in some cases, can be computed by solving some Bethe-Ansatz equations. There's some recent work. So is this also the case for half indices and quarter indices?
I think that depends on the supersymmetry. So if you, so 0,4, I think a Bethe-Ansatz, yeah, right. So yeah, for example, I think so if you introduce certain line defects, then they will satisfy certain difference equations. Then maybe we can understand, yeah, such, like asymptotics of the behavior of the index, and maybe Bethe-Ansatz can work some, Bethe-Ansatz also related to some superpotential in this case. But I mean, this is a case with enhanced supersymmetry, not n equal 2 for XCD series. Yeah, but I don't know, maybe interesting.
Okay, thanks.
Is there any other question? Okay, I stop the recording and let's thank the speaker again.